All right, so now what we're going to do in this session is just go through the chapter 5 problem set. So I've chosen 24 representative problems, all of which we could use some practice with. So in some of these cases, it's very straightforward, but in some cases, you may have to consult with the notes to find some of the rules that you realistically can't be expected to memorize them all. For example, you may need to check out the table of integral formulas for trigs and that type of thing. But once you've found the right formula, there's no reason why you can't get these right. It's just that sometimes you have to manipulate them into the right form in order to see what approach you should be using. Anyway, let's get to it. So first of all, we have 5 log x. And by the way, it says at the top here for these first 3, we're going to just simply take the derivative. So for example, here, now, if you remember, the derivative of the log of x is just 1 over x. Okay, the derivative of the log of a function of x is a little bit more complicated. Now here, you notice there's a 5 multiplying by this log x. So this is not actually, this is not log g of x. Okay, it's simply 5 times the derivative of log x. In other words, you notice what I've done is I've factored the 5 out and then taken the derivative of just log x. Okay, and so by doing that, we'll end up with a very simple result. 5 times 1 over x, which is 5 over x. Okay, so in other words, it's not the case that we're looking here at log g of x. It's simply 5 times the log of x. On the other hand, if you look at the second one, you'll see that this time we really do have log g of x. In this case, g of x is 2x squared plus 1, and therefore g prime of x, based on the power rule, is 4x. So we'll borrow this rule from up here, and we'll see that what we have is, it's down a bit, the derivative of log g of x is g prime of x over g of x, or 4x over 2x squared plus 1. And since there's no obvious way of simplifying this, we'll just leave it like this. All right, so far so good. Oh, now look at this disaster. Now, this is one of those cases where you have to look at it and say, is there something I can do to simplify it before I try to find the right rule? Because what you actually have here, it's not just a function. And by the way, you notice that the independent variable here is t. The letter doesn't make any difference. You can have t, z, whatever. What matters here, though, is that, yes, this is log of g of x, or g of t, rather, but we may be able to simplify things by taking advantage of the properties of logs. And well, like in this case, for example, you notice how we have a product and we also have an exponent. So if you recall, the log of a times b is the same thing as log a plus log b. The log of a divided by b is log a minus log b. And then the log of a to the r power can be written as r log a. So we're going to need these properties. In fact, I think you'll see if we apply these properties, we can make things a lot easier for ourselves. What I'm going to do is rewrite this as first, let's write, since there's a product here, let's do it like this. Why don't we try this? Okay, Now, what we did was we rewrote this equation using logarithms, but now I think you'll agree that finding the derivatives of each term separately and then combining them will be easier and quicker than trying to attack this one directly. So in this first case, this is simply 1 over t. Now, what about the second one? All right, well, here, think of this as g of t is t squared plus 3, and therefore g prime of t is 2t. So what I've actually got here is 3 times. Now remember, the way that rule works is that the derivative, if it's t, it would be log g of t would be g prime of t over g of t. So here I'll have 2t over t squared plus 3. And of course, we can just multiply the 3 by that entire expression. And so we ultimately end up with 1 over t plus 6t over t squared plus 3. Now, of course, there's other ways we could write this, but like we could try to combine these into a single term, that type of thing, but we might as well just leave it like this. It's fine. Okay. There's no point in making unnecessary work for ourselves. Now, here's an interesting one. Logarithmic differentiation. Well, what is that all about? Well, what we're going to do is we're going to take the log of both sides. And the reason why usually the only reason to do this is to make it a little simpler for ourselves. If it doesn't, there's no point, but it does specifically ask us to use logarithmic differentiation. So let's do that. And then at the end, we can confirm it by simply using the product rule. Okay. So let's see. Now, of course, the whole purpose of doing this is to use the properties of logarithms to make it a little easier to take the derivative. And here, what I'm going to do is rewrite this as log x squared plus 1 to the 1/2 power, which I then will write as 1/2 log x squared plus 1. Now, again, we're confronted with a couple of very straightforward derivatives. So keep in mind, though, that when we do this, the derivative of log y is equal to dy dx times 1 over y. Okay, this is the important detail. If you forget about that, you're not going to get the right answer. So the derivative of log of y is dy dx times 1 over y by the chain rule. Now here, this one will just be 1 over x. Now here, we do have the log of g of x. So the derivative will be g prime of x over g of x, which means 2x over x squared plus 1. Okay, so in other words, if you have g of x equals x squared plus 1, and g prime of x is 2x. So that ratio is this. And now we can simplify it a little bit. These two cancel each other out. And if you want, you can combine those into a single expression. Now, oh, I almost forgot. I almost left out this one. Now, that's important, this part, because now what I've got to do is multiply both sides by y. We'll go back and get the original definition of y, and then plug it in. And if you recall, that was equal to x radical x squared plus 1. And then again, if you feel like it, you can go ahead and simplify this, but this is the actual answer. Okay. Wow, that's a messy answer. Now you can see why, sometimes this is helpful, but you know what? Let's see what would have happened had we simply gone ahead and said, we know how to do the product rule. Let's give that a shot. So remember how that works. Which means here g of x rather is x. G prime of x is 1. H of x, I'm going to write it as x squared plus 1 to the 1/2 power. So we have to be careful here because h prime of x requires us to use the chain rule. Now that's a little bit messy because you've got it's basically, this is sometimes called the generalized power rule. You're multiplying 1/2 times the entire expression. Then you have the exponent, you subtract 1, and then this is actually the derivative of what's inside here. Think of this as g of x and g prime of x. So anyway, when we plug these in, we'll have x x squared, x squared plus 1 to the 1/2 plus, wait, oh, I'm sorry, I did something wrong. Let's try that again. I need g h prime of x. That's what I was missing. Plus h, which is x squared plus 1 to the 1/2 power times g prime of x, which is simply 1. All right, so I have, by the way, if you notice, there's some cancellation going on here. There's two x's, so I've got x squared plus 1 to the minus 1/2. Okay. So, if you want to algebraically manipulate it, you'll see that they are the same thing. But, sometimes the log approach works better. Sometimes the direct approach, like this one, works better. But it's good to know that we have at least two different ways of getting to the same result. Now, what's going on with this one? Ooh, okay. Well, we can certainly use the quotient rule here, but it may be that there's something quicker than this. Oh, actually, I just realized we're supposed to use the log differentiation for this one too. All right, let's do it with log differentiation. And of course, right off the bat, you can see that we can simplify this a little bit. We can differentiate each one individually. Now this one, this is g of x. G prime of x in this case happens to be 1. So when we differentiate this, the log y becomes dy dx times 1 over y. This is just 1 over x. Now this one is going to be g prime of x over g of x, which means 1 over x plus 4. Okay. And now we just multiply both sides by y. And then remember, y was originally x over x plus 4. All right. I mean, if you want to multiply that, you can. And if you do that, you'll get this first term would be just simply 1 over x plus 4. The second term, be x over x plus 4 squared. And then if you wanted to, you could multiply this by and so you're going to end up with x plus 4. So now we have a common denominator, and we end up with so. And again, if you want to do a double check, you can apply the quotient rule. Because maybe you don't think you did it right. So, or maybe you'll want to get some practice. All right, so let's do this. Let's just quickly double check this with the quotient rule. All right, so then g prime of x will be 1, as we saw. Actually, well, interestingly enough, h prime of x is also just 1. So that should simplify things quite a bit. In fact, it definitely simplifies things. That reduces very nicely to 4 over x plus 4. So that means, yes, obviously we did it correctly. All right. Now we get some integrals. Now these, if you look at them carefully, you'll see most likely there'll be logs involved. So for example, now look at this one. Well, there's a couple of ways we can go about this. You could rewrite this as, and then you could use u substitution. So, like again, there's always so many ways of going about these problems. So yeah, we could do it with direct u substitution. And if we do, we have du over u. And that means we have log u absolute, don't forget the absolute value. And we're all set. And also, of course, don't forget the c, because this is an indefinite interval. All right. But when you see something like that, you've got a constant in the numerator and a function of x in the denominator, not as x squared, but just x. Chances are there'll be a log in there somewhere, because the derivative of x is simply 1. So, give it a shot. Try u equals the denominator and see what happens. Now these are a little bit messier, but you know what? Now here's the key to the whole thing. The highest exponent in the numerator is lower by 1 than the highest exponent in the denominator. And that's often a hint that we're going to wind up with a log. Because if you look at this, let's try u equals 5 minus x cubed du dx is minus 3x squared. We don't have that. We have x squared. So we can rewrite this as Nothing's changed by multiplying by negative a third and multiplying by negative 3. I certainly end up with the same result. And so now all of a sudden I have minus a third du over u. Oh, whoops, I almost forgot. Don't forget that constant. I did just forget the constant. Negative a third, natural log absolute u plus c, and u this time is 5 minus x cubed. Right. And similarly, the eighth number 8 will be the same idea. If you notice here in the numerator, x squared is the highest power of x cubed in the denominator. So why don't we try this? Let u equal x cubed plus 6x squared plus 5. And u dx will therefore be, based on the power rule, 3x squared plus 6x. And du equals 3x squared plus 6x dx. Now, do we have that? No. But if you notice, we're close. Because if you multiply this numerator by 3, what happens? 3, what do you know? 3x squared plus 12x all over x cubed plus 6x squared dx. So guess what that leaves us with? Our favorite result, 1/3, and we like this result because it's so simple. And there it is. Now, we didn't get so lucky with this one. Oh my God. Now, once you get involved with trig functions, you'll probably need to consult either the slides or the book for the formulas. But here, if you notice, we can think of this as u equals x over 2 and that means we do need to supply the 2. Or the 1/2, I should say. So you notice I haven't changed anything. I multiply by 2, I multiplied by 1/2. And so what I end up here with is 2 secant u du. Okay, now, unless you have these memorized, if you go into the book or the slides, see, there it is. Integral of secant x dx is this. So we can rewrite this as, just replace the x's with u's. So that would be log secant u. Sorry, log absolute secant u plus tangent u. And of course, we don't need, actually, we do need the constant. And then what we do need to do too is remember, we defined u to be x over 2. And there we go. All right. Oh, look at this one. Now, by the way, when you see something like this, what you might want to do is rewrite it as, which you're perfectly allowed to do. If you notice, I factored the 2 out of the first one because it's a constant. The first one is easy. It's the second one we have to worry about. So let's look at that for a second. Now, this one is very similar to the one we just got through doing. because what we can do is let u be x over 4. And du is 1/4, or we can think of that as du is a 4th dx. All right, so great. So this one now becomes, oh, actually, no, we need one more step. That means we're missing the 1/4. So let's rewrite this. So again, nothing's changed. I multiply by 4 and multiply by 1/4. And so what's good about this is I now have 4 integral tan u du. And what does that give us? Tangent u brings us to negative log cosine, absolute cosine. I remember u was defined as x over 4 plus c. Now, we're not done yet because what I just did here was just solve the integral of the tangent of x over 4. We still have to deal with this 2 times the integral of dx. So we're going to wind up with and then this is just 2x rather, 2x. All right, and now we're done. So by getting involved with that tangent, it would be easy to forget all about the, oh, I almost forgot the absolute values. Yeah, in other words, we spent so much time with the tangent. Don't forget about this first part, this 2. It needs to be there as well. So you have 2x minus 4 log absolute cosine x over 4 plus c. All right, now look at this one. Now, it looks like a nightmare. But you know what? Oh, that's right. E to the log of g of x is simply equal to g of x. So this expression is nothing but 3x equals 24, which means x equals 8. So it's almost a trick question. Yeah, that's right. A trick question. All right. Now these these are derivatives involving e to the some function of x. So remember how that works. Okay, so here it's e to the minus 8x. So we'll let g of x be minus 8x. The exponent of e will always be the g of x. And then g prime of x will be the negative 8 by the power rule. So we end up with, and by the way, don't forget, this is an example of the chain. So we're going to end up with e to the g of x, g prime of x, meaning e to the minus 8x times minus 8. And if you don't like it the way it looks, aesthetically, it might be more pleasing to write it as negative 8 e to the minus 8x. Of course, it doesn't make any difference. God. So what else do we have here? We've got these are pretty similar. Well, at least this one is. Then it gets a little trickier. Um, so here it's f of x is 5e to the x squared is 5. So the 5, we can sort of keep it on the outside of all of our calculations. Let g of x be x squared plus 5. G prime of x is 2x. So what we end up here with is we'll have the 5 first and then e to the g of x, g prime of x, e to the x squared plus 5, 2x. Or if you prefer 10x, e to the x squared plus 5. That does look nicer, doesn't it? But now, now you can see here that we're going to need the power rule. Sorry, the product rule, no matter how you look at it. So let's do this. So remember, so let this be g of x, and this is h of x. So g of x is x, g prime of x is 1, h of x is e, or x, and then by the chain rule, we just got through using h prime of x is 4e to the 4x. Anyway, so let's use the product rule. Let's see. Great. Now we just do some substitutions. And we'll have x 4e to the 4x plus e to the 4x times 1. All right, so it looks like we'll be able to consolidate this one because we've got 4x e to the 4x plus e to the 4x. And if you feel like it, you can rewrite this as, it might look a little nicer. Now we're getting into some deeper waters. There's some rules that we went through. Like here, for example, we've got a constant raised to a function of x. If you recall from the slides, this is probably in part 5b. Let's see if we can find it. Oh, wait, I think I found, no, those are integrals. We need derivative. We're getting close. Here it is, the derivative of a to the g of x, which is exactly what we have here. So the way the rule works is that the derivative of a to the g of x is log a to the g of x, g prime of x. It doesn't matter what order you write these, obviously. Yeah, okay, it's slightly different here, but it's a to the g of x, log a, g prime of x. So now we just do some substitution. We have log 6, 6. Sometimes it works. 6. Yeah. It gets cranky sometimes, this tablet. 6 to the g of x, 6 to the 3x minus 4. And then we need g prime of x, which is 3. So, let's clean it up a little. This is all one constant. That's our coefficient. Okay. All right. How about this one? Ooh, now this one has a log other than base e. So there's a rule for this one too. All right, so we need a rule for the derivative of log a g of x. Okay, let's go find it. There it is. Well, what do you know? It's g prime of x. All right, so here we have a is 3, g of x is x squared minus 3x. G prime of x by the power rule is 2x minus 3. We're going to have 2x minus 3 log 3 x squared minus 3x. Okay, and it's pretty clear that we can't simplify this, so we'll just leave it like that. All right, what's going on here? So they want us to use logarithmic differentiation. Okay, so now the rule that we need here. Oh, actually, what we should probably do is this. Because then we just have a constant times x. All right, that's going to work a lot better, I think. We differentiate. So the derivative of x times log 3 is just log 3 then. We multiply both sides by y. And remember, the original was 3 to the x, so we just have 3 to the x log 3. Now, there is a rule in the slides, if you want to confirm this, which says that the derivative of a to the x is a log a, which actually, hold on. Let me go find it. Okay, so in other words, a to the x becomes a to the x log. Oops, sorry, I left this out. Okay. So, in other words, which implies that the derivative of 3 to the x must be 3 to the x log 3. So in other words, whether we use logarithmic differentiation or not, we're still going to get to the same result. Okay, great. That's how you know that you've done it correct. All right, now back to integration. Now, you know what's interesting? Well, that was just a wild coincidence. If the derivative of 3 to the x is 3x log 3, that implies that the integral must be Okay, but suppose that ridiculous coincidence didn't happen. How would we have known this? All right, well, here's how it works. Again, there's a formula in here somewhere that tells us, and let's see if we can go find it. Um, no, those are derivatives. Oh, wait, it's right here. Here it is. It's 1 over log a to the x. Let's see. So in this case, we would have e to the x dx. E is 3, of course. All right, it's here we go. Oh, that's it. Yes, that's it. So either way, we've got the right answer. Now this one, you can see, it looks like a catastrophe. There can't be a rule for this, can there? No, there doesn't need to be, because here's what we're going to do. Ah, well, the first one is easy. We can just apply our power. So the first integral is easy. The integral of x to the fourth dx is simply x to the 5 over 5 plus c. What about 5 to the x? Well, we just got through doing one like this. So remember, just a couple of minutes ago, we did integral a to the x dx equals 1 over log a plus c, of course. So that means this one is going to give us 1 over log 5 to the x plus c. So when you combine these, final answer will be x to the 5th over 5 plus 1 over log 5 to the x plus c. We only need the one constant. Okay. Now, here's one. We haven't seen this in a while. It's a definite integral. Where have you been? We missed you. Okay. But what kind of problem is this? It's g of x because it's x over 4. And so if you go back to the slides, what's here? Um, oh, you know what? We may not need it. I'll tell you why. Because this, well, technically, yes, this is a function of x, but it's just a constant being multiplied by x. So let's try this. The 1/4. We're missing the 1/4 that we need to make a du. So let's apply it ourselves. So what we end up here with is 3 to the u power du. Okay, so that means we end up with 4. So it's 3 to the u as the integral. Remember up here, oh, God, I almost left it out. I still need 1 over log 3. That's better. That was a close call. I almost left out the 1 over log 3. Because if this is true, which we know it is, that implies that the integral of a to the u du is 1 over log a to the u plus c. Okay, so you're just replacing x with u, which is itself a function of x. So that, now, by the way, that log 3 is a constant. So I'm going to rewrite it as 4 over log 3. U from way back was x over 4. And since this is a definite integral, we have to evaluate it. Okay, so we'll have 4 over log 3. So I'm replacing, this is what we have previously called f of 4, capital F that is, and this is minus 4. And that just means you go into the result and you replace, wait a minute, what just happened there? I think it erased stuff on. Yeah, that's just what I wanted. All right, let's try that again. Okay, so let's do this. So this is 3 to the first minus 3 to the minus 1, which you could rewrite very simply if you want to as 3 minus the third. You can try to consolidate that into with common denominators. I feel like it. You could, for example, write this as 9/3 minus 1/3, and then you end up with 32 over 3 log 3. That looks a little cleaner. All right. Now we're back to L'Hopital's rule. All right, so let's try the first one. So first, if direct substitution works, then you don't need to bother with L'Hopital's rule. So let's see what happens here. Okay, so that is one of the indeterminate forms that can, when it results, we are allowed to use L'Hopital's rule, which means that we can do is calculate instead of this ratio, we replace it with the derivatives. Okay, great. So f of x is the numerator, which is x squared plus 9x plus 20, which means that f prime of x by the power rule is 2x plus 9. G of x, the denominator was x plus 4. And so therefore the g prime of x is 1. So now our new limit is 2x plus 9 over 1. And that reduces to 1. And we're done. Very good. It's very satisfying when such a mess like this turns into something straightforward. Oh, now we got trig. All right. Well, let's do direct substitution. Now, if you go to your calculator, you'll see that the sign of 0 is just 0. So we're going to try L'Hopital's rule here. So f of x is sine 6x. Now, we have to be careful with this. By the chain rule, f prime of x is going to be sine, if f of x, sorry, is sine g of x, then the derivative will be cosine of g of x times g prime of x. So here we're going to have, and clearly g of x is 6x. So g prime of x is 6. So this leaves us with cosine 6x times 6, or 6 cosine 6x. That would be the derivative of the numerator. And so denominator is 4x. Oh, so then, of course, we're going to rewrite that as f prime of x over g prime of x, thanks to our friend L'Hopital. And then we'll have 6 cosine 6x over 4, just 4. And then when you plug this into your calculator, the cosine of 0 was actually 1. So which means 6 times 0 is, of course, also 1. So it's going to end up being ultimately 6 over 4, or 3 halves. Right. The arc sine. All right, so this is in the slides. This is a function of x, by the way. So what we're going to do is write it like this. Now, I know there's a chart in here. Here it is. Let's take this. So in this case, g of x is this x minus 1. Oh, wait, what am I doing? So this is our g of x. And therefore, g prime of x is simply 1. So according to this rule, we'll end up with 1 over radical 1 minus x minus 1 squared. Okay, if you wanted to go through the steps, algebraically, this is the same thing as 1 over radical negative x squared plus 2x. Okay, but of course it's the same thing. And then finally, we get this one. Now, just by looking at it, you can probably see, recognize that pattern. It's almost certainly one of those arc sine, cosine, whatever functions. Let's take a look at these. This is an integral now, so let's jump to that list. Here we go. So it looks like it's going to be a squared minus u squared in the denominator. Let's grab this one. With the understanding, now here's where we have to be careful though. If a is 1, a squared is 1. If u is 2x, u squared is 4x squared, which is fine. But then we need the du dx would be 2. So we need to supply that 2 to fit this into this form. So we're going to write it says 1 half 2 dx. So what we have here is du over the square root of a squared minus u squared, which you can see at the top here is going to be 1 half arc sine u over a plus c. Now we just substitute back. U was 2x and a was 1. We're done. Oh, and plus c. Don't forget the c. All right. So, wow, that took a long time, but I mean, we got them all. You can see now, some of these do require you to go back to the slides and look up some of the formulas, but the key to the whole thing is recognizing what type of problem each one is. That's really the challenge. And also, of course, keep in mind that in all of these cases, really, there's typically going to be more than one way of getting to the same answer. And so unless it explicitly asks for a specific technique, you can feel free to use whichever one you want. Okay. You might find that one technique is more comfortable than another, or it makes more sense to you, and so do it. All right. There's no point in making unnecessary work for yourself or confusing yourself. Just do whatever it takes to get to the right answer. All right. Wow. So anyway, now we're done. So what's coming up next is, remember, we're not doing chapter 6. We're going to look at 7, which is a brief look at some applications of, we're actually looking at ways of using these techniques to solve for specific types of problems, which involve physical values like volume and surface area and things like that. So we're not going to spend a whole lot of time with that discussion, because what comes after that, chapter 8, is a huge discussion about some of the many different techniques that we can use to take integrals. And I think that we should really spend most of our time with chapter 8, because it's going to come in so handy in Calc 2 and Calc 3. The more you know about integration, the better off you'll be. There's so many techniques we could use. And so what I'd like to do is just quickly get through chapter 7, and, we're going to do it, but we don't want to spend too much time with it, because like I said, unless you're studying mechanical engineering or something, you won't really need those techniques as much as you will need chapter 8, where we learn all these amazing integral formulas and techniques. So that's where we're heading. And when all that's done, fairly soon we have to start thinking about some kind of final exam, I guess. This time around, we'll probably try to use the technology, the lockdown thing that they have, but we'll work on that. So right now, just focus your attention on these chapters, and then fairly soon, we'll start thinking about what to do about a final exam. Okay. All right. So I'll see you next time.